So let's talk about the PaaS stack. Now we're going into that layer, and this is really the GPU PaaS stack and what is being offered. So I'm Shaun O'Meara, CTO at Mirantis. Let's talk about the PaaS. So in that very first diagram, I showed you some of these AI-enabled services that our neoclouds, our cloud providers can offer to their customers that we have out of the box. So a couple of those things, the key ones, obviously, we've just showed you managed Kubernetes as a service, virtual machines, GPU and CPU. This is the very basic that everybody needs to be able to provide. And then bare metal servers. So they can then stack up a combination of all of these for a single tenant and provide services for those tenants. Where it starts to get more interesting is what are the basic inference and cloud services that they want to offer to their customers that start to create a richer PaaS experience, GPU PaaS experience for their tenants. So we have inference as a service. We have several solution offerings around inference as a service. But essentially, that is a tenant UI that they can come in and they can launch an inference service and start to have their own private LLM or a LLM from Hugging Face or one of the other public catalogs. We maintain our own model catalog within the tenant. Again, it's an OCI-based registry. Those models live within that OCI-based registry.
It's based on Harbor, is that?
It's based on Harbor.
I always thought Harbor was more of a container catalog than a model catalog.
There is a move towards supporting it. There's a lot of work happening within the open source community to better support models and support the OCI layering to deliver models that way. It does involve specific setup within the core network to ensure that you can get the performance out of it, and we do that setup by default. Mostly it's the way that models are presented to the hosts. If you're trying to do a traditional Docker pull on a 600 or 4 gig file, you will wait until time immemorial because it's a single-threaded pull. So we use alternative mechanisms to make that available, mostly NFS, to make them available immediately to the host so they can start immediately. Jupyter Notebook as a service, managed Slurm. So there's a big drive towards running Slurm on top of Kubernetes clusters. So we're leveraging this operator to be able to deploy managed Slurm on top of Kubernetes clusters. Again, it's stacked up using the services portal. And we have MLflow as part of our offering. As one of those service offerings, we have Kubeflow, and we offer some fine-tuning capabilities.
What's one of the drivers you mentioned there of Slurm on top of all of this? I mean, it's an enterprise ask or a CSP ask, or what's there?
It's being driven to reduce the complexity. So the CSPs are doing it because bare metal management is a pain. A big NVIDIA node like that, one of these big 8 GPU nodes, takes 50 minutes to reboot. Mm-hmm. And if every time I want to put a new tenant on top of one of these things and I've got to do a full reboot of the underlying node or nodes, and when I have 32 of them or 64 of them, et cetera, it's hours and hours and hours of work to switch over. Mm-hmm. Whereas if I have just a Kubernetes cluster, even if I put just one VM across all these nodes and interconnect them, I'm massively reducing that time to switch the cluster over.
Gotcha.
It's also just simpler from an operational management point of view. I no longer need complex LCM systems to deploy the Slurm components and lifecycle them. It's just a Kubernetes, and then I run everything using Kubernetes norm.
So it's essentially pushing a good part of the management plane local, right?
Think of Kubernetes as a new generation Puppet or Chef, or it's really starting to become that.
Yeah.
Probably more like Chef in the declarative way Chef worked, but now I'm starting to show my age. I wanted to bring back to this whole idea of the state management component and these service templates that we spoke about, because this is important for how we actually deliver this underneath the hood. We use these templates, which are a collection of different templates that provide for different capabilities. And we can support different types of deployment mechanisms. So we could use Helm charts, we can use raw Kubernetes manifests, we can use operator-based deployments, all the complexity of that management is put into these templates. And we'll actually show you a demo, time permitting, of a very complex service that requires multiple dependencies being deployed at one click. including the cluster component. We can then version control. We've spoken quite a bit about the version controlling, this idea of immutable templates that then have template chains that control the life cycle of the template. And really importantly, we can do dependency management. Because as much as we all love the fact that Kubernetes is eventual consistency, it's not actually always perfect. You sometimes need to put things in a specific order.
How do you maintain the dependency graphs?
It's done within those template chains.
Okay, are they built manually or
they're built manually?
Okay.
Oh, speaking of chains, how do you implement the chaining?
It's part of the function of the coordinate operator, and then we have a CR that defines the chaining. It's a YAML file again.
That's what I was hoping you would say, yeah.
It's a YAML definition again.
Well, it's all YAMLs all the way down.
Yeah, it's YAMLs all the way down, but those YAMLs are held as CR objects.
Well, you made it sound like you actually could do like GitHub integration or
yes.
some other source code control integration.
So this is where the tool KTL comes into this. So KTL allows us to do the GitHub integration, but if you're using, say, Argo, Argo has a Kubernetes CR plugin, and it'll handle that whole lifecycle for you. In fact, we use Argo for some of our deployments. There is a component deep in the stack where we can actually reference GitHub directly as one of the configuration options for the raw Kubernetes manifests.
Okay.
And then we can also control what GitHubs you have access to, because they have to be registered with the system. You can't just randomly create a Kubernetes object pointing at a GitHub. So that's how we also handle the whole air gap complexity.
Where's something like model versioning and data versioning fit into this framework? It's not quite state management.
So it sits primarily in the OCI registries for us. So OCI, having an OCI registry is a requirement to do this. We obviously offer our public OCI registry. We offer that for our customers and especially our enterprise customers. But most environments will deploy their own local OCI registry. In fact, we recommend it. And again, we have our own, but many of our customers have Artifactory or other OCI solutions. We even have ones using our competition's versions of it, which is fine. We'll integrate quite happily.
Yeah.
OCI is a standard. This is standards based.
When you were talking about GitHub, is it GitHub only, or is it
Git?
Git, okay. So anything that can supply an API token, speak the right language. Okay, cool.
So it's interesting, that one. I don't want to rabbit hole too much, but security and security management of all of these different provider endpoints is one of the things that we're actually solving for in a consistent way as part of Coordinate. Because the whole identity credentials management is really, really complex to get right. And we're solving that. And that's actually driven by those provider templates we spoke a little bit about earlier. But that's a deep, deep rabbit hole that we could use the entire 2-hour session for. So we spoke about the integrated catalog. Kevin covered this in depth, but essentially we have a catalog of services. It's public, catalog.coordinate.io. Go and have a look through it. We're constantly adding to it. We have enterprise partnerships with a lot of the people in the catalog, but a lot of those are open source and available for anybody to use. We also have the ability to have private elements just within the customer catalog and still show this within their operator UI. A demo, and I won't steal too much of Anjelica's thunder, but this is culminating in this whole chain that we're talking about of building a cluster solution, putting the services on it, and actually launching an end user customer. Now we're showing you the detail in the meat here, but from an end user customer point of view, all they would do is go to that portal and click the button, and they would get the end result. So over to you.
All right, so in this next demo, we'll deploy an inference cluster template with the Coordinate platform. So here we have several cluster templates ready for a use. So we have most fields are in simple drop-down menus, allowing for customization based on your needs. So let's go over to our GPU nodes. So you can configure your GPU nodes depending on the types of AI or HPC workloads you plan to use your cluster for. And then let's go ahead and skip over to which services you wish to deploy with the cluster. So here we have a list of cluster services. For the sake of this demo, we're going to
go back a little bit quickly. I just want to point out something here. So one of the things which and I'm sorry to interrupt this, one of the things I just want to call out, if you look at the template, the sort of standard templates we were showing you earlier, I wonder if we can get this just a little bit further back. There we go. Our sort of standard templates, you'll often see there's only one or two types of worker types. What we've done here is, because we need more complex and more options of different types of workers, that template has been created to have multiple different types of workers. And so in this deployment scenario, what we have is we have control plane for the Kubernetes cluster. This happens to be, part of the Kubernetes cluster. We have a hosted control plane model, which actually abstracts the Kubernetes cluster control plane, which I didn't talk too much about. But then we have different types of GPU nodes as well that can be configured within the environment. Now, this is going to be deployed at AWS.
Taking that from AWS directly?
Yes.
Okay. So
the point here is, from a cost management point of view, if I just go and create all GPU nodes, that isn't sane from the point of view of a cost management point of view, because I have a lot of things that will never need a GPU within these clusters. Now I can actually start to create different profiles within a single deployment of a single cluster. And that's quite a critical point when we start to look at, especially when we go into public cloud, but even in private and even in the cloud service provider environments, because they often have much cheaper infrastructure for running CPU-only workloads. And that can give them a whole different profile. Sorry, Anjelica.
All right, so back to where I was before. We're going to add the Run.ai services and its dependencies. So what we do is that we deploy this with the cluster, so we can access the Run.ai portal via the cluster details page. And I can demonstrate this here. So once we click on the cluster details, we can actually scroll down and access the Run.ai portal here. So let's go ahead and navigate to our Run.ai portal. We can view the running inference workloads, as you can see on screen. So this just shows that in just a few clicks, we've deployed a cluster capable of handling AI workloads with supporting services to deliver GPU-backed inference and more. This is a typical workflow, but we have the flexibility to deploy any type of services depending on the requirements.
What we're trying to demonstrate there, and in a very quick and simple way, is this ability to deliver a very complex set of services with very minimal overhead. And once that's done, we can now maintain the lifecycle of those services. And we can deliver that anywhere. It doesn't just have to be within a single service provider's environment.
You deployed there had both Kubernetes worker nodes as well as GPU nodes.
Correct.
Specific workload components would be allocated to the GPU
Correct.
nodes versus the workload based on the requirements.
Exactly. So underneath the hood, built into the templating, is the labeling, the correct labeling of those nodes. And then that happens to be Run.ai, but the Kubeflow does it as well. Run.ai can then validate those labels, and it will only provision workloads to the correct types of nodes. That's also then automatically, because there are 9 dependencies to Run.ai in this particular case. We need cert-manager, we need the GPU operator, we need, well, the whole list is here. We can actually just pop back to it. Where's that list now? Pause it here. We need the ingress, we need Argo, we need Prometheus stack, we need Knative, and the Knative operator. All of those have to be put in and configured before you can even get Run.ai to start. Now, I'm using this as an example, but the thing is here, because all of those are coming as a single cluster of templates, we call them a composition of templates, all the user has to do is select that I want that service, and the rest of those templates are put into the system. And it takes, full disclosure, it takes about 15 minutes to spin this up on AWS. 14 of those is waiting for the AWS machines to start. Yep. This is including all the certificate keys, collecting the information, downloading all of the objects if they're not local. And of course, we can do it all air-gapped as well.
So many of those, just educational purposes, many of those container activities do not require GPU, and they would be allocated to worker nodes ones that require GPU, the back end, GPU operator, et cetera, those would be specifically loaded on the GPU server
Correct.
nodes.
And you could have multiple different types of GPU nodes. So you could have, for example, L40s, and you could select nodes with H200s. And we can see that, and you can select that through the UI in this particular case. Now, we're demoing this on AWS because we can quickly and easily get access to the GPU infrastructure. The same is true on-prem. If you had KubeVirt underneath the hood as your virtualization layer, or OpenStack, or VMware, we can do the same, or frankly, bare metal. Now, if we were provisioning this to bare metal, it would take a little bit longer. But the end result is, and in the UI, you actually see a runner from the end user point of view, which we didn't really touch on that heavily, but you actually see a runner with all the stages of what's happening, so that you don't end up just watching a ball roll for 15, 20 minutes waiting for something. You can actually see what's happening.
So if you're using the SaaS platform for the management plane, and then you've got bare metal or virtualization resources on-prem, what's that thing that's giving the connectivity from the management plane back down to the on-prem? Do you have an agent of some form that runs?
The operator, the provider for AWS, which is part of CAPI, is constantly reconciling. It does a loop reconciliation, which is validating.
Well, I'm not talking about AWS. I'm talking about when you've got something on-prem.
Same idea. The operator is constantly reconciling. So it talks to the APIs for the service. Let's say it was KubeVirt underneath the hood, or OpenStack. It's constantly reconciling against those APIs to validate the current state and providing that back. Underneath the hood, we have a number of watchers that watch the various layers and then provide that information back. And then that is then presented up into the UI.
Right, but you still, I mean, you're behind a firewall on-prem.
Yes.
Okay, and you don't have connectivity from that management plane that lives somewhere out in the cloud directly through that firewall to something else. There's got to be some kind of runner there that can actually build the bare metal.
Yes. Okay. Now I understand the scenario you're talking about. If the SaaS-based control plane is outside, yes, there is a secure connection back. The on-prem runner connects out to the controller.
Okay.
And it
So
uses
that's deployed as a VM or as whatever?
As a whatever you have on-prem. So it needs a small Kubernetes cluster.
Okay.
And a kube cluster, cluster can be a single node.
Right. Got it.
It runs our K0's distribution of Kubernetes, which has Cosmotron as part of it. And we can even have the control plane running in the cloud as long as we've got low enough latency, which we generally do in modern world. We can actually have this Kubernetes control plane running up somewhere else, some magical resource place, and the worker can be running anywhere. In fact, one of our teams has just for the fun of it done some testing and run Kubernetes clusters on an airplane with a control plane sitting in AWS. And we all know what airplane, I think most of us spend a significant portion of our lives on airplanes, what the performance is like.
Okay.
So if we jump a little bit into the future of where we're going, thank you. Today at Mirantis, we're here. We're focused on IaaS and the GPU platform as a service layer. And we're rapidly evolving through that. As we're moving into the future, we're moving into the AI PaaS platform. And this is moving into the agentic integrated MCP stack and creating DAG and workflow and enterprise level security and structure around agentic and AI workloads. And we're doing some rapid work in that space. So watch that space, that's coming from us. And I'm going to close with this. I promised I would do a little bit of a shill here. Our vision for the future of infrastructure for applications is around contracts for performance of infrastructure. Okay? What we're talking about here is instead of defining infrastructure from the point of view of, I need so many GPUs, I need so many CPUs, you're starting to set a performance criteria that is matched by the infrastructure application environments. And the infrastructure will take care of servicing the correct resources and even determining if you've asked for the correct resources. That's the vision. That's the long-term vision for the future. And this is where we're driving towards with this whole vertically integrated stack. Horizontally integrated stack to give those resource guarantees before I trip over myself here. So thank you very much.
Just a quick question on that. How exactly do you intend to do contention analysis on these architectures?
Contention analysis.
Yes, if you're building out large cluster architectures, you have the potential for contention points.
So right now, we're primarily heavily instrumenting the environment and collecting a lot of that instrumentation. We're starting to experiment with intelligent models that can look at that data. Some of them have been built by some of the big players and are public. Mostly it's by design today. We have to manage by design and have alerting for those environments. We're hoping to bring more intelligence into it in the future. But we don't have a really easy answer for it right now.
Okay, you don't have any method of doing modeling ahead of time to...
With the work that NVIDIA is doing today, for their specific reference architectures, we can leverage some of the tooling that they're doing. Right now, I don't have a pre-modeling mechanism, no. What I am hoping to build in the future is a digital twin of the environment.
Okay.
But I'm going to be very open, that's forward-leaning.
Okay.